So after learning about the first crucial piece of calculus, limits, we now know how to look for the value at a point by approaching it with values that are very close to this actual value. And this leads us to another idea involving infinitesimals, which is one of the two main features of calculus. So, to start with the problem that plagued physicists and mathematicians in the 1700s, we'll look at a line like this. So, how can we find the slope of this line at this point? Well, it's pretty obvious. The slope of this line is just rise over run. So, delta y over delta x. And this is the formula for the average rate of change between 2 points, right? So, you're right, m, the slope, equals delta y over delta x, rise over run. That's pretty simple. But now imagine we had a graph that looked something like this. The graph of y equals x cubed. How can we find the slope of this? Because the slope of around here is basically 0. If we draw a line tangent to that, the slope around here is clearly very positive. So what's going on here? How can we actually find the slope at any given point here? So I'll remove these lines to make it easier to see. But this is a big problem in math. You need to be able to know how things change, which is the whole idea of calculus. So we can start by thinking of in terms of the average rate of change. So let's say we wanted to find the slope at x equals 2. How can we do that? Because the slope is changing as you go along the line, along the curve. So what we can do, we can make an approximation. Say we find the average rate of change between the point at x equals 1 and the point at x equals 3. So this is what we call a secant line. So this is a pretty good approximation, but it's not great because the tangent is a little steeper in reality. So I'll take these away again so you can see. But to find the average rate of change between 3 and 1 and find the slope of the secant line, we just use what we learned in algebra classes. We'll do delta y over delta x like we did before. So 3 cubed minus 1 cubed over 3 minus 1. And then that'll be 27 minus 1, which is 26, over 2. And 26 over 2 is 13. Now, that's just an approximation. That's not the actual slope of the line at this point. So, if we want to get really close to the actual slope, we can use a better approximation. Say we use 2.001 and 1.999. So then we can do 2.001 cubed minus 1.999 cubed divided by 2.001 minus 1.999. So when we do this, we get that the slope, which we'll label m for now, that'll change later, we get m equals 12.0000001. And the real value is actually just 12, but this is a very good approximation. However, it's a little annoying to calculate. You have to get out your calculator, and this is just not an efficient method for more complicated functions that are not just polynomials. So people like Newton wanted to find a way to make this very exact. So he started by writing out a general form of this average rate of change idea. So if we draw a graph of something that looks like this, then we want to find, let's just say again, the slope at x equals 2. We can define the average rate of change between 2 points. So this and a point over here. This is a secant line, remember. This is a poorly drawn line. So the slope of this we can get from, and let's call this little distance here, delta x. And this new y value up here, f of x plus delta x, which is just the y value delta x units away from 2, which is what we want. So the formula for the average rate of change between these 2 points will be f of x plus delta x minus f of x divided by x plus delta x minus x. And then if you notice, these x's just cancel, and we're left with just delta x at the bottom. So this is a general formula for the average rate of change between 2 points. But Newton wanted to make this an instantaneous rate of change, not just an approximation using the average rate of change. So what he did is he revolutionized math, and he made it so this was the limit as delta x approaches 0. So that means that this little delta x over here gets very close to 0. So if we redraw our graph down here so it's easier to see, that means that this delta x is getting really close to 0. So this is a better approximation than this point. It's a better approximation. And then as it approaches 0, as this delta x approaches 0, we approach the real value of the slope of this function at that point. So the general form of this is the limit as h approaches 0. H is just the same thing as delta x of f of x plus h minus f of x over h. And if we just plug in h equals 0, we'll get f of x minus f of x over 0, which is 0 over 0, and that doesn't work. So the limit, this limit is what we call the derivative. So we'll call this dy over dx, which I'll explain right now. This dy dx notation just symbolizes that, if we draw our line again, that if we have this point here, if we take a really, really small nudge to x, call it dx, which is the same as delta x, what's the resulting dy between these 2 points? Dy, the change in y, which is the same thing that we wrote up here, right? So this ratio is the same thing as rise over run. It's the slope of the line, but using very, very small nudges instead of like 1 or bigger changes. So using this nudge definition, you can plug in very, very small values like we did earlier, and you'll get really, really close to the real answer. And as you make h approach 0, you get really, really close to the real answer. So now we have to think about when you can actually take the derivative of a function and when you can't. So the important things are when you can't. So as we learned in the last unit with limits, if something is not continuous, then you cannot take the derivative of it. It's called non-differentiable. So if you have a function that looks like this, there's a hole here, and then the function continues this way. Since this is not discontinuous, it's also not differentiable. It's also not differentiable. And a function can also be not differentiable if it's something like an absolute value function and it goes up and then it just curves down. And then there's a point there that's not, where the derivative just changes really quickly and it's not smooth or something like this. This is differentiable because this here is nice and smooth. But if the derivative changes really subtly, like that, then it's not differentiable also. So now a very important rule that you're going to use throughout all of calculus is something called the power rule. So the power rule mathematically says, says that the derivative, d over dx is how you write the derivative of f of x, a function. Let's call the function x to the n. So it's a polynomial. Or in this case, it could just be x cubed, x to the 4th, x to the 20th, anything. Equals, the exponent comes down, so it'll be n times x. Then you subtract 1 from the exponent. So x to the n minus 1. Okay? This is very important. You don't need to think about this formula every time you're using it. You can kind of just think of, like here, the exponent's hopping down, and then you're subtracting 1 off of the exponent, right? Okay, and another property of derivatives is that if you're adding two things, like let's say you had x cubed plus x, and you wanted to take the derivative, you would take the derivative of x cubed, and then separately the derivative of x. So the exponent would hop down, you'd have 3x to the power of 3 minus 1, which is 2, 3x squared, plus, if we think of x as x to the 1, then the 1 hops down, it's 1 times x, so that's just x, and then 1 minus 1 is 0, so then it's x to the 0, which is 1, so 3x plus 1, and this is the derivative of that. And then another property is that if you multiply the derivative of something times a constant, is you can just take the derivative and move it outside. So if you had 3x cubed, you can ignore this 3 when you're taking the derivative, and then just take the derivative of x cubed. So 3, and then 3x squared, like we did earlier. And then you take away this line, and then you do 3 times 3x squared, which is just 9x squared. So if there's a constant in front of something you're taking the derivative of, you just multiply the exponent by the constant instead of just bringing it down. And then another important thing to note is that the derivative of a constant c, that could be anything, that could be 1, 4, 7, anything, is just 0. Because if you think about a constant as being, if you think about 4 as being 4x to the 0, then the 0 comes down, and you have 0 times 4, x to the negative 1, and then that's just 0, right? So the derivative of any constant is just 0. And then the next thing we want to think about is how do we take the derivative of functions that are not polynomials, like x to the n? Well, there are a few special cases where this could happen. So one case is a trig function, right? Like sine of x. You can't just use the power rule and bring down the exponent. It has to be different. Now, there is a proof of this derivative, but it's not really that important for you to understand for this class. So I'll link a Khan Academy video that explains this in more depth. But for now, all you need to know is that the derivative of sine of x equals cosine of x. The derivative of cosine of x is negative sine of x. And then the derivative of negative sine of x. Remember, we can treat the negative in front as like a -1 constant. So then you just take the derivative of sine, which is cosine, and then multiply by -1. So negative cosine x. Now another special derivative, which is a lot easier to memorize, is you remember that number e that equals like 2.7 something, right? Well, in calculus, it actually becomes important and you get to see where it comes from. So the property of that, what some consider the main property of e, is that the derivative of e to the x equals e to the x. It equals itself. So that's really important for some things where the derivative is proportional to itself, but we'll get to that more in Unit 7. So this is an important derivative. It'll come up a lot. And then the same rules, if it's multiplied by a constant, then you just take the derivative of e to the x and then times the constant. So if you have 2e to the x, derivative is still just 2e to the x. Same thing. And then the last special derivative is the derivative of ln of x, which is sort of related to e to the x. So the derivative of ln of x equals 1 over x. These are, it's helpful just to memorize these. It's not, you don't really need to know where they come from for the exam, but if we look at what we have the derivative of sine equals cosine, derivative of cosine equals negative sine, derivative of e to the x equals e to the x, derivative of ln x equals 1 over x. Okay, there will be a couple more trig derivatives that we'll go over at the end, but these are the most important ones that you should definitely know. And then the next thing is another thing that we won't really show the full derivation for. I can link a video in the description that I think is helpful if you really want to understand where this comes from. But in reality, you're not really going to need to derive this on the test. You can just apply it. So there's something called the product rule. Forgive my handwriting. Which states that if you have the derivative of something like, let's say you have x times cosine x. You can't just take the derivative of that because you're multiplying, not adding. Remember, if we were adding these, you could just take the derivative separately. But because we're multiplying them, we have to use something called the product rule. So let's say f of x equals x. This is this part. And then g of x equals cosine of x for this scenario. These could be anything. So the product rule says that the derivative with respect to x of f of x times g of x equals, there's like something that can help you remember. It's left d right plus right d left. So this is the left one and this is the right one. And another notation that I should have showed you earlier, which is very important, is that we write the derivative of f of x as being f prime of x. So this little prime just means the derivative of. So that's going to show up in this formula. So I'll write another equal sign down here to make it more clear. So the derivative of f of x times g of x, in this case we're doing x times cosine of x, is the left one, f of x, times the derivative of the right, g prime of x, plus the right, g of x times f prime of x. So look, left d right plus right d left, because g of x is the one on the right, f of x is the one on the left. All right, so this is something that you just have to internalize. You multiply the derivative by the other function, and then you add the same thing but where you flip them. And if we take it for this specific problem where x is f of x and cosine of x is g of x, then we have left is x times the derivative of the right, which is negative sine of x, plus right is cosine of x, times the derivative of x, which is just 1. So then your derivative of this will just be negative x sine of x plus cosine of x. Now let's say you had to find the derivative of a function at a point. So let's use this function just because it's convenient, because we already did it. Let's say we wanted to find the rate of change, the slope of a tangent line, at x equals 1. Well, then we just take our derivative function. We can call that f prime of x, is this. And then we can take f prime of 1. F prime of 1. And then you just plug in 1 wherever there's an x. So f prime of 1 equals negative 1 sine of 1 plus cosine of 1. Now, 1 isn't the best number to work with for sine and cosine, but this would be your answer, negative sine of 1 plus cosine of 1. And then this could work for any function. If you need to find the slope of a tangent line at a single point, then you just plug in whatever your x value is into your derivative. And something that's pretty similar to the product rule is the quotient rule. So this is the same idea for when to apply it, except instead of f of x times g of x, you have f of x over g of x, so when you're dividing something. So the formula for this, again, is a little annoying to memorize, a little more than the product rule even, but you can remember it as low d high minus high d low all over low low. So we'll see what that looks like. Let's say our function is x to the fourth over e to the x. So it'll be low g d high, so times f prime of x, minus high d low f of x times g prime of x, all over low low, so g of x times g of x, which is g of x squared. So this is the general formula for the quotient rule. And now if we apply it to our particular case of x to the fourth over e to the x, we do low is e to the x times d high, derivative of x to the fourth, is 4x cubed, minus high d low, so x to the fourth times the derivative of e to the x is e to the x, over low low, so e to the x times e to the x. And now we can simplify this a bit. We can factor out an e to the x from the top, and then we're left with 4x cubed minus x to the fourth over e to the x times e to the x, and then these cancel, and then we're left with our derivative dy over dx being 4x cubed minus x to the fourth over e to the x. And then again, like with the product rule, we can just plug in any point and then find the slope of a tangent line at that point. And we just plug it into this formula for the quotient rule. So now we'll look at a few more trig integrals other than just the simple sine and cosine that we saw earlier. So we're going to make a little table, which it'll become clear in a second why the table is useful. But let's just write out our trig functions: sine, cosine, tangent, cotan, secant, and cosecant. Notice that we're putting the co-functions on this side and then all the other functions on this side. So we know that the derivative of sine is cosine and the derivative of cosine is negative sine. So those are the simplest ones. You should remember those. Those are going to come up a lot. The other ones won't come up quite as often, but you still will need to know them. So now the bottom two rows are where the table really starts to come in handy. So tangent of x, the derivative, is secant squared of x. So it's this squared. It's the one below it squared. And then for secant, it's just secant times tangent. So secant x tan x. So it's the one that you're doing times the higher one. And now it's the same thing on the right, except all the cofunctions are negative. So like cosine is negative sine, so cotan is also negative. And if we use the same rule from over here, it's this one squared, so negative cosecant squared x. And then cosecant, just like secant, in this case it's negative itself times the higher one, so cotan. And then these are all of the main trig integrals that you're going to need. I mean, not integrals, derivatives. So these are the most important ones, but you should also have a grasp of the other ones below it. So now this is where College Board likes to divide between units 2 and 3. So unit 2 is basically just an introduction to derivatives, and unit 3 is more complicated derivatives. But they're basically the same idea, so I'm grouping them together, and it's a lot simpler to teach. So we'll make another area for unit 3. So the first thing in unit 3 that we have to learn is something called the chain rule, which comes up all the time in calculus. So this happens when we have a function inside of a function. It's like nesting dolls. So if we had f of g of x, or you may have seen it written like this, like fog, f of g of x. So to take the derivative, it's not as simple as just like f prime of g of x, because g of x is not just x. If it was f prime of x, we wouldn't have to do anything, right? But since the g of x is replacing the x here, we're going to need to add an additional step. So for the chain rule, you take the derivative of the outer function, so f prime, and then you leave the inner function as is. You leave it untouched, but then you multiply by the inner function's derivative. So let's say we had something like this. 3x cubed plus 2 all to the fifth. So notice this isn't just x to the fifth, and it's not just 3x cubed plus 2. It's kind of a mix of both. The 3x cubed plus 2 is inside of something to the fifth. So we'll define our f of x to be x to the fifth, and then our g of x to be 3x cubed plus 2. So we'll bring the 5 down onto the outside, so it'll be 5 times, we leave the inside unchanged, and then subtract 1 from the exponent, and then multiply by the derivative of the inside. So the derivative of 3x cubed is 9x squared due to the power rule, and the derivative of 2 is just 0. So then this is our final derivative using the chain rule. And it's a little easier to remember than the other ones just because you just have to multiply by the derivative of the inside. And if you have multiple iterations of the chain rule, you just keep multiplying by the derivative of the inside. Now another example of this would be something like cosine of x squared, where you'd first take the derivative of the outer function, cosine, and then you get negative sine of x squared. But then since the x squared is not just x, it's not just sine of x, you have to multiply by its derivative, so times 2x. And then this is your derivative of cosine of x squared. Now, one idea that this leads to is the idea of implicit differentiation. Now, I know that sounds really complicated, but it's basically just derivatives, but instead of for functions like f of x equals something, it's for things that include both x and y. So if we remember from Algebra 2 when we learned conic sections, let's say we had something like x squared plus y squared equals 9. It's just a circle with radius 3, something like that. Now this is not a function because, as we see, it doesn't pass the vertical line test. These vertical lines don't only have one value corresponding to each x value. But we can still take the derivative. Like if we look over here, a tangent line still exists. So how do we find it? Well, we start by just taking our definition of how we write a derivative. So dy over dx. That's the derivative of y with respect to x, right? So when we take derivatives, we know we can just take the derivative of x normally. So that'll be 2x plus, and 2y is a little bit different. So y itself is a function, right? Like that's what it always is. F of x and y are usually interchangeable. So it'll be 2y, but because y is the function, we have to multiply by its derivative. But what's its derivative? Well, it's dy dx. By definition, that's what dy dx means. It means the derivative of y with respect to x. So times dy over dx. And then equals the derivative of 9 is 0, because it's a constant. And then if we rearrange the equation a little bit for dy over dx, we get negative 2y dy over dx equals 2x. And then we end up with dy over dx equals negative x over y. Now, something that I should have shown a little earlier is how to use the derivative to find the tangent line, not just the slope of a tangent line, but the actual equation for a tangent line. So let's use this as an example. So let's say we wanted to find the equation of a tangent line at the point 1, 3. Okay, well, first we plug in 1 and 3 to the slope because it's dependent on both x and y. So x is 1, so it'll be negative 1, and then y is just 3. So negative 1 over 3. That's the slope of your tangent line. Now, to write out the equation, we just go back to point-slope form from algebra. So it's y minus y1, which is 3, equals negative 1 over 3 x minus x1. x1 is 1 here. And then when we rearrange a few things, we get y minus 3 equals negative 1 over 3 x plus 1 over 3. Then add the 3 to the other side, and we get y equals negative 1 over 3 x plus 10 over 3. And this is the equation of our tangent line, not just the slope. This gives you exactly where it is as well as its slope. So now before we get to a few more memorization heavy things, I think we should start with this thing that's a little more intuitive and easy to grasp with what we've already done so far. So this is something called higher order derivatives. So we can first think of this by thinking of what the first derivative is. So we have f prime of x is the same as dy over dx, whatever. That's the first derivative. But what if we wanted the second derivative? Taking the derivative again, well, it's just f double prime of x, and then d squared y over dx squared. Well, now what if we wanted to keep going? We could just take more and more derivatives. We want to find the rate of change of the rate of change, the second derivative. Well, we can do that. Let's say we have f of x equals 3x to the fifth. Then f prime, the derivative, is going to be 15x to the fourth because of the power rule, right? Now, let's say we want to take another derivative. We have f double prime equals 60x cubed. We want a third derivative, we can do that too. F triple prime of x equals 180x squared. And we can do this as many times as we want until we have the derivative that we're being asked for. Now, sometimes a little bit of a more complicated question with this is that they could ask you for the nth derivative. So this usually happens when there's like a pattern when you're taking derivatives. So it'll be a little clearer with an example. So let's say you're asked to find the nth derivative of e to the 2x. Well, the way that you go about doing something like this is you first start by taking the derivative once and seeing what happens. So the derivative of e to the something is just e to the something. Then you multiply by the derivative of that something because of chain rule. So the derivative of 2x is just 2. So now your derivative is 2e to the 2x. Now what if we wanted the second derivative? We can take another derivative. Then we just multiply by 2 again because of the chain rule. Everything else is the same, and we just have to do chain rule again. So 4e to the 2x. If we notice, every time we take a derivative, we're just multiplying by 2 again because of the chain rule. So we can write this as 2 times the number of derivatives we take, n, times that same e to the 2x. And then this is our solution for the nth derivative of this term. This is a pretty uncommon question, but it's important to be prepared just in case it happens to come up on the exam. So now another thing that we have to know, which is a little bit less important for understanding calculus, but you still have to know it, and it's a little memorization heavy, but it's how to find the derivative of an inverse function, f negative 1 of x. So there's a formula for this that you kind of just have to memorize, and it's 1 over f prime of f inverse of x. I know that's a little bit annoying to look at, but it's what we have to deal with. So I think it's best to see this in an example. So let's say we had f of x equals x to the fourth plus 5. Let's say g of x is the inverse of f, so f negative 1 of x. And we know that g of 6 equals 1. So now the question is, what is g prime of 6, which is the same thing as f negative 1 prime of 6. So what does that equal? How would we go about doing this? So what we can do is we can plug it into this formula over here. So then we have 1 over f prime of g of x. So we know that we know that we're looking for g prime at 6. So we can plug in x equals 6, right? So then we have 1 over f prime of g of 6. And then because we're given g of 6 in the problem right over here, we can just plug that in. So then we have 1 over f prime of 1. And then if we go to f equals x to the 4th plus 5, right? So the derivative of that is just going to be 4x cubed. So if we evaluate that at x equals 1, then it's just 4. So the derivative is 1 over 4. Now let's say we weren't given this original point that like g of 6 equals 1. So let's say we had just f of x equals x cubed plus 3x. And we wanted to find f negative 1 prime of 4. Now we're not given any initial point or anything. We just have to work with this. So the first thing we want to do is find f negative 1 of x, right? So if we remember from our other classes, we have to switch x and y for each other, right? So then we have x equals y cubed, that looks like an x, y cubed plus 3y. So now we want to solve for what the y value is, because we only have the x value as being x equals 4, right? So we need to find the y value so we can plug that in. So now we have 4 equals y cubed plus 3y, right? And now if we solve for y, we get y cubed plus 3y minus 4 equals 0. Now if you plug this into a calculator and solve for y, you'll get that y equals 1. And if we remember about inverse functions, if we have the point 4, 1 on our inverse function, then the point on our original function is just going to be flipping the x and y values. So it'll be 1, 4. So this is f negative 1, and this is f. So now if we go back to our formula, we have 1 over f prime of f negative 1 of x. We can make that 1 over f prime of f negative 1 of 4, which is 1, as we can see over there. So now what's f prime of 1? If we go back up to our original function, we see that it's x cubed plus 3x, and its derivative is 3x squared plus 3, right? So f prime of x equals 3x squared plus 3. And now if we plug in 1, we get 3 times 1 squared plus 3, and that's just 6. So the answer is 1 over 6. Now I know I said I was leaving the memory heavy stuff for last, so this is a little bit memory intensive because you have to memorize this formula, but this thing is really just memorization. There's not really a lot of understanding that goes into it. But it's inverse trig integral derivatives. So it's like the derivative of sine negative 1, or equivalently arc sine of x. So this is very rarely going to be on your AP exam. If it is, it'll be like one question. So don't stress about it too much if you can't remember this. I'll just write these out in case you decide you want to remember them. My teacher didn't teach them, but if you think it's important to understand these, then you should copy these down into your notes. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. The derivative of cosine negative 1 is negative 1 over 1 minus x squared square root. And then tangent negative 1 is 1 over 1 plus x squared without a square root. Then there's cosecant inverse, which is negative 1 over absolute value of x, square root of x squared minus 1. These are just very annoying to work with and to remember. They don't, like other things, they don't really help you understand calculus. They're kind of just something that you're tested on because that's what College Board likes to do. So secant is then 1 over absolute value of x, square root of x squared minus 1. Same thing as up here, but without the negative. And then lastly, there's cotan inverse of x, which is negative 1 over 1 plus x squared. So if you want to take like a screenshot or something, these are your inverse trig derivatives. And this is pretty much the last topic that you need to know for units 2 and 3 and the entirety of derivatives, the concept of them. The next 2 units will cover the applications of this concept. But yeah, this is a pretty good review before you start diving into calculus. So once you start learning units 4 and 5, then you should tune into my next video that I have about those, and hopefully I helped you understand this concept a little better and from a more conceptual perspective, despite all the annoying formulas that you have to memorize.